Hello everyone. This week we are going to take a look at a tool called a t-test. And a t-test is essentially the ability to compare means. Now I'll go into a little bit more detail in these slides and give you some examples of when we would want to do that. But probably the most clear example is when you have two separate groups and maybe one group has undergone some sort of treatment or some sort of exercise, and you want to test those two groups on the same variable. Let's imagine it's SAT scores. You've got high school students from one high school and high school students from another high school. In the second example, those high school students went through some preparation process for the SAT. So now what we've done is we've administered the SAT, they've gotten their scores from the SAT, and we're going to compare them to see if they're different. If they're extremely different, there's a couple things that could be causing that. It could be outliers. You have a couple students that performed extraordinarily well, and that's throwing off the average. Or it could be that the intervention that you had, the preparation for the SAT, was actually had quite a bit of an effect. It was a significant enhancement to how the students performed on that test. But we want to know that. We want to know if that is in fact the case. The problem with t-tests is we're starting now to get into some of the tools that have a little bit more complexity. So I will try to present this as straightforwardly as I can, and I will only present the options in JASP that are ones that you need to concern yourself with. Other ones you can look up on your own and figure out if you want to learn about those, but we're not going to talk about those today. So I'll kick this off with just some basic concepts. And I got to get to the right screen here. There we go. Okay, so what is a t-test? So like I said, we're comparing the means of two samples to see if they are different. So we could just calculate the means and see if those are different. But remember, means are derived by the scatter. They're impacted by the scatter around the mean. So if there's a wide scatter around the mean, then that's going to impact the value of the mean. If there's a very narrow scatter around the mean, that's also going to have an impact. So we can't just look at the means themselves. We have to also look at how scattered are the data points around the means. And that's what the t-test really does for us. So here's an example. And in this sample, I've got two samples. The first one, I've got the values 37, 42, 39, 45, 48, and 41. And in the second sample, I've got 39, 41, 47, 42, 36, and 65. When I calculate the mean of sample 1 versus sample 2, the mean of sample 1 is 42, and the mean of sample 2 is 45. So right away, I can tell you that the means are different. But what I can't tell you is that difference significant? Okay. Well, why do we care? Well, imagine you have got these three scenarios. The first one, you've got two groups. And these two groups are groups of employees. Let's imagine they're groups of employees. One of them was trained using an in-class training process, and the other one went through an online training process. Now, as the HR director or the leader of these teams, I want to know if the end result is different, if it's significantly different. If it's not significantly different, then it doesn't matter which class I use or which modality I use. But if it is significantly different, then I may want to make some decisions about how I train my employees. So, are their scores different significantly? And if so, what does that say about our training modalities? Okay, that is a t-test known as an independent sample t-test, which basically is two groups. I'll go into this more in more detail in a bit. Two groups on the same variable. Okay. The second example is we could test our group. Say we test them at the beginning of the year, and we put them through a 4-month training course. And then we test them at the end of the year. So did the training make any difference? And that's what's known as a paired sample. In a paired sample, we have the same group. The pre and the post are the same people, the same subjects, and we get two measurements, one from each subject. And so we get a pre-measurement and a post-measurement, and then we calculate the mean for all the pre's and calculate the mean for all the posts and run it through a t-test and determine if the difference is significant. Again, that's paired sample. The third example we have, imagine we have 100 students at our university and they took a standardized exam. Say they're getting ready for grad school, so they took the GRE. Their average scores, when we look at them, the average scores that we got back gosh, they seem relatively high. And I want to know, just from my own edification, and also that because it says quite a bit about the way we educated them, are those scores for those 100 students, are they significantly higher than the average score that is out in the whole national population? So that is what we call a one sample t-test, because we only have one sample. We're only looking at the mean of one group, but we're comparing it to something we know, a value that we know in the population. So the three types of t-tests: we have the independent sample, where we're comparing two independent groups. We have the paired sample, where we're comparing two measurements of the same group. And then we have the one sample, where we're taking the sample, calculating the mean, and comparing it to a value that we know in the population. And here's more detail on each of these. So again, independent samples, two groups, no repeats across the two groups. So they're two completely independent groups. We're measuring both groups on the same variable, and then we're comparing those means. With paired sample, we have one group, but we have two measurements. And it's typically a scenario where we have a pre and a post, and some intervention that occurs in the middle. And so the test tells us something about our intervention. Do the means differ from pre to post? And then the one sample, we got one group, no repeats. We're comparing the mean within my group to a known value in the population. So is my group statistically significantly higher or lower than what we know about the population? There are different types of t-tests. The most common, and you may have already heard of this one, is the student's t-test. And the student's t-test can be run with either an independent scenario, a paired scenario, or when you have just one sample. So all three of those that I just went over in the previous slide, you can use student's t-test for any one of those scenarios. There are reasons why we would and reasons why we would not want to use a student's t-test, and I'll talk about that next. The Wilcoxon signed rank can be used with the paired sample or the one sample, and there are reasons why we would or would not want to use that one. And then the Welch is only available for the independent sample, and again, there are reasons why we would want to use Welch over student's t-test. Okay, so which one do we use? Well, when we do t-test, there are a couple of assumptions that we have to meet, and if we don't meet them, then we can't use the most common t-test, which is the student's t-test. The first assumption that we must meet and prove that we meet is that the data is normally distributed. What that means is if you were to take the mean value of all of the subjects in your data set and plot them on a grid, it would look like a bell-shaped curve. It would have a normal distribution with a mean at the middle, which would be the top of your curve, and then it would curve down smoothly on both sides, looking very much like a bell-shaped curve. That is an assumption that we make if we want to use the student's t-test, which is the most common one. Okay? The other assumption that we must meet is that there is an equal variance. And what that basically says is that, remember, the variance is, for each data point, the distance away from the mean. So we calculate the mean, and then we go through every data point in your data set, and we calculate the variance. What we want to see is that variance for all 100 or 1,000, however many data points you have, is pretty close. There's not a lot of variation in that variance. So if that's the case, then we meet the test of variance. But if we have a big chunk of data points that have a really high variance and a big chunk of data points that have a really low variance, we don't have what we call an equal variance or an equally distributed variance. So that would be something that we would have to take into account. So let's assume, going back and reviewing this slide, let's assume we pass both of these tests. The data is normally distributed and there's an equal variance. We can use the student's t-test in all three of our examples, whether it's independent, paired, or one sample. If either or both of those assumptions cannot be met, then we have to use an alternative test. The alternative test does not presume that we have normally distributed data, and it does not presume that we have equal variance. So here are, I'm going to actually go back on this one. So here's what we can do. So let's assume we meet our two assumptions, that normally distributed and equal variance, student's t-test, we're good to go. Okay. If we do not meet either one of those tests, then for the paired sample and the one sample, we can use the Wilcoxon signed rank test. It does not presume normal distribution or equal variance. But for the independent scenario, the Wilcoxon is not available. We use Welsh instead. And you'll see that when we get into JASP. You'll see that we have multiple tests that we can use. There are other tests that are available. I'm not going to go into those. I just wanted to make the point that now we're trying to pick the best test for the data set that we have. And we'll know something about our data set. First of all, we'll know what kind of t-test we're going to run, whether it be, or what kind of sample we have, whether it's independent paired or one sample. And then we'll go ahead and run our tests for normal distribution and for variance. And if we pass those, we do the student's t-test. If we don't, we do either Wilcoxon or Welsh, depending on the type of data that we have. Okay, how do we know if we pass the assumptions? How do we know if the data is normally distributed or if it has equal variance? Well, there are two tools built into every scenario that we have in JASP that will tell us that. Normality is a test, and it's just an option that you check, and we'll look at it when we get into JASP. But it was created by a couple of statisticians, Shapiro and Wilk, back in 1965, I think, something like that. That is a test that tells us if we are normally distributed. The assumption is that all data sets are normally distributed. But when you run the Shapiro-Wilk test, and if it comes back with a p-value less than 0.05, then we have to reject that assumption and assume that our data are not normally distributed. Levine created a test for equality of variance, and that's an option available to us in JASP. Again, the null hypothesis is that the variance is equally distributed. If we get a data, or if we get a p-value back on the Levine test that is less than 0.05, then we can assume that our data do not have equality of variances, and we need to use an alternate test. So the normality test and the equality of variance, if both of those come back with p-values greater than 0.05, then we're good to go with the student's t-test. We don't have to worry about normality or equality of variance. But if either one or both of them come back with a p-value less than 0.05, we have to abandon the assumption of normality or the assumption of equality of variance, or both, and use the alternate test that's available to us other than the student's t-test. Okay, let's take a look at this in JASP. So I'm going to go ahead and see if I can't get into... I should have this queued. Here we are. All right. So first things first, we're going to go ahead and open up a data set. And we're going to just take from their sets, their data library. We'll go down to t-test. There's several data sets that they have created for us and given us so that we can use them in the t-test. And then we'll pick up the directed reading activities. And what I'm doing here is I'm following chapter 8 in your textbook. He goes through these in a lot of detail. I did, however, want to go through those tests of testing the assumptions and the like, and how that drives what test you're going to choose. He goes into it as well, but he's not great about introducing the test of assumptions. So that could kind of throw you for a bit of a curve, but if you've watched this video, you'll understand what we're doing. So I'm going to go ahead and open that up. This basically is I'm going to use an independent test on this. And the reason why is because I have some number, I don't even remember what, I think there's 50 measurements, something like that. Some of them are treatment and some of them are control. So the variable I have is, that's how I'm going to split it out, is group. The variable I have, the actual value is the DRP. And then G, I believe, is also split. It's just a second way. It's a numerical way of splitting out the group. So I can go through probably, I don't know which one he uses. Anyway, so we're going to go ahead and go into t-test. And we're going to do the independent samples t-test. Remember, this is when we have the same variable, but two independent groups. And I'm going to split this out by G, and that's going to be my grouping variable. And there's a whole bunch that we're able to see. So let's start with what we first got. We compared the control and the treated, indicated by 0 and 1, for the DRP variable. And the DRP variable over here in our table shows us a t-statistic of 2.267, which is fine. Our degree of freedom is 42. Degree of freedom is the amount of, basically it's the amount of data points minus a few. I'm not going to go into the calculation of how we do that, but there's a reason why we do degrees of freedom, and I've talked about it in a previous video. And then our p-value is 0.029. Assuming that we're using a threshold of 0.05, this is a significant result. Okay, it shows us a significant result. But we have a couple things we need to do first. First of all, we got to come down here and look at our assumption checks. The first one is normality. The second one is equality of variances. If we check normality, it's going to give us the Shapiro-Wilk test. And remember, we're looking for any scenario where we have a p-value of less than 0.05. We do not find it here. So our assumption that the data are normally distributed holds, and we're good with the student t-test. Okay. Now let's go down and check for equality of variances. We have the same thing here. Our assumption that the variances are distributed equally holds because our p-value is greater than 0.05. So both of these tests told us that we can use the student's t-test. Okay? If we could not use the student's t-test, we can come in here and we can use Welch. Welch does not presume normal distribution or equality of variances and is able to give us a result without making those assumptions. Our alternate hypothesis is that the two groups are not equal. Okay. Well, based on this p-value, this alternate hypothesis holds. We can accept that alternate hypothesis. We could also say that the group 1 is greater than group 2 or group 1 is less than group 2. We're not going to go into that right now, but just know that those options are available to you, and we would get a result that showed us that. The other thing that we want to look at, there are two things I want to look at. One of which is going to be the effect size, and we're going to use the Cohen's d. It defaults to the Cohen's d. Cohen's d is the effect size, and what it does is it pops this little value up here. And Cohen's basically is trying to show us what the impact of the treatment was. In this particular case, remember we had control and we had treated. We've already determined that the results of those, the means of those two groups are different. But now we're trying to get some sort of value, some sort of idea of just how different are they, right? Just what was the impact of the treatment? Essentially, as we're interpreting this, what was the impact of the treatment on the group? A Cohen's d of 0.64 is a moderate difference. It runs typically from right around 0 all the way up to as high as 2.0. And in this particular case, we're getting 6.684. That's a moderate change. It's typically 0.2 is small, 0.5 is moderate. Anything around 1 or even higher can either be big or, as some textbooks put it, huge. So in this case, it's not. It's okay. And then the other thing we want to look at is descriptives. Descriptives just gives us a table of our two groups, group 1 and group 0 and group 1. How many data points do we have in each? What were the means of the different groups? The mean of group 0 was 51.476. The mean of group 1 was 41.522. We have our standard deviation. We all know what a standard deviation is. It gives us two other variables as well. And I'm going to go a little bit into them, but I wouldn't concern yourself too much about them. The coefficient of variation is your mean divided by your standard deviation. And then the SE, which is basically the standard error, is a way of being able to assume or assess how much or how close your sample is to a population. So again, don't worry about them too much. It's just not that. They're not that useful. We're not going to use them that much. Okay. Okay, that is the first example that we have. This is our independent samples t-test. The next thing we're going to do is we're going to bring a new data set in. We're going to go ahead and open. We're going to go into data library, go to t-tests, and in this case, we're going to bring in moon integration. Opens our data file for us. And here's what we're looking at. Remember, this is paired. So we have person 1, person 2, person 3, all the way down to person 15, right? And what we have is we have the number of aggressive or whatever troublesome incidents that happen when there's a full moon and when there's not a full moon, right? And so we want to know if the mean of the number of incidents for when there is a full moon is statistically significantly different than the mean when there's not a full moon. Okay, so we're going to use the paired t-test, paired samples. Okay, here are our pairs. We can bring over moon, we can bring over other, and that's our pair right there. And are they statistically significantly different? Well, right now we're defaulting to students t-test, but our t-value is pretty high. Our degrees of freedom is 14, it's basically n-1, and our p-value is less than 0.01. So we have a statistically significant result. I would question this because there's only 15 entries, there's only 15 people, so that tends to throw things off a bit. If your sample's bigger, then that would be better. Down here we only have one assumption. For a paired test, we only have one assumption, and that is that the data would be normally distributed. Let's take a look at that. The data is normally distributed. Remember our result of our Shapiro-Wilk test? We only need to worry about it if it's 0.05 or lower. In this particular case, it is 0.148, so the assumption of normality holds, and we can stay with the student's t-test. We'll come down here and turn on effect size, which we don't. Oh, it gives us a Cohen's d, that's fine. And that's 1.666. That's a big one. That's a large effect size. So apparently the moon has a very large effect. And then we can pull in our descriptives, and we get the same thing. We get the standard error, the coefficient of variation. Again, these are basically just measures of dispersion. How scattered are the data points across the mean? But we already have that with a standard deviation. We have the mean for the moon, we have the mean for the other, standard deviation for both, and we kind of get the picture here, right? So that is a paired, we have two instances, the moon and other, for all 15 of our subjects, and these are the results that we get. Okay, we're going to go in and bring in our data set again. I think we're going to use the same data set. I think it will let me do this. Data library, t-tests, directed reading activities. Okay, and in this particular case, we're going to treat this like it's an independent, right? Remember, with the independent, we only have the one sample. So we're going to ignore the fact that we have treatment and control and just look at the DRP. And DRP is the measure of, it says it in the textbook, but I don't remember what the acronym, but the reading skill, basically. So we'll go ahead and click on one sample t-test. Okay. The variable we're going to look at is going to be the DRP. Okay. It's telling us right away that we have a pretty high t-value. We have 43 degrees of freedom. We have a p-value of 0.00 or less than 0.001. So that is telling me that we are significant. But significant against what? What are we actually looking at here? Well, down here there's a test value, right? And in the textbook he shows you that if you go in here and you set this to what we know in the population, right? This is the measurement in the population of all students across the country. Then we're going to get a different result. We're going to get a different result because now, instead of comparing it to nothing, we're comparing it to this kind of population score of 51. And so our DRP mean actually significantly different than 51. It still tells us that we have a t-value. It's a negative t-value, but t-values can be taken as absolute values. Degrees of freedom is the same, but our p-value is substantially different. 0.046. We're almost outside of the realm of significance. So we're pretty close to this 51, close enough. I mean, we're far enough away that we have a significantly different result, but still a lot closer than when we didn't have anything there at all. We haven't looked at our normality checks, so we can take a look at our normality check, and it checks out. Okay, so we're going to stay with our students t-test. If our normality p-value had dropped below 0.05, we would choose the Wilcoxon signed rank, and it would give us pretty much the same thing. It just does it in a different way and gives us a more reliable result. Our effect size, our Cohen's, is negative in this particular case, which basically means that Cohen's d can be negative given the order in which you are comparing your values. What this would tell me is that the DRP average that we have is in fact lower than 51. It's not higher, it's lower than 51. So because that's why we have the negative Cohen's d. It's slightly lower than 51 is what that effect size is telling me. And then the descriptives doesn't really give us a lot because there's only one sample, right? So we had 44, the mean was 46.273, again, lower than the 51, which accounts for the negative Cohen's d. Standard deviation, we have our standard error, and our coefficient of variation. So that is pretty much all I wanted to show you on the student's t-test. Again, in all three cases, we could do the student's t-test. But again, when you check one of these, it will give you the other test. It just gives you different values, right? So the effect size is very close. The p-value, in this particular case, probably not significant using the Wilcoxon test because we're above 0.05. And then the statistic is just calculated differently than the student's t-test calculates it. So that's what the difference would be, is if you were doing a one sample or a paired sample or an independent sample and you choose one of the other boxes, then you'll get both results. You just have to decide based on your assumption checks which one you want to pay attention to. Okay. This week's assignment, I'm going to give you 3 files. Your 3 files are going to be an independent file, a paired file, and a one sample file. And I'll give you 3 scenarios, and I want you to load up your data into JASP. I want you to produce results. I want you to report on your results and put that into a Word doc just like you always do, and have that be your assignment for this week. If you have any questions, let your instructor know.